All right, so hello and welcome back, everyone. Today we're going to be talking about slope stability, and you'll immediately notice that one, the slide is square, two, it looks old, and three, it's not by Dr. Sears. It's by Dr. Keith Heasley. Dr. Heasley was one of my professors as an undergraduate. He was also my master's and PhD advisor. So what you're getting today is going to be exactly what I was taught in class about slope stability. So, here we go. Mine slate slopes that are subject to failure. Number one, high walls. And you can see that in the background. Also, waste dumps, right? And that can be coarse refuge or like an impoundment or a dam for a waste dump. Stockpiles, so you have piled up coal. That's actually pretty common, especially if you're working dozers on the stockpile with underground feeders that have a tendency to create voids in the pile. You can end up like this, which has historically been very bad, typically fatal. Although nowadays, you can see on this dozer here for sure that there is a steel mesh screen that's put up around the window. So, the way these dozers are set up nowadays, you have wire around all the windows so that they don't get either shattered or pushed in from the surrounding coal if you were to fall in the stockpile. And then also they've equipped these dozers with self-contained self-rescuers so that the driver has access to air, and that's made this situation tremendously more survivable than it was, say, in about 1997. Tailings dams or impoundments. So you've created this slope out of material, and you've now impounded stuff behind it. So those are also subject to slope failure. So how significant is the problem? In a 4-year period between 92 and 96, there were 22 slope failures. Fortunately, we've gotten a lot better at designing for slope stability, and this has obviously gone down. However, there have been a couple of recent events, not in the U.S. I believe one of them was in Brazil, and one of them was somewhere in Africa. That's the most recent. Tailings dam failures. I'll put a couple of those videos up on YouTube. I've seen a few out there that sort of show the scale of and complexity of what all's going on. But so they still do occur, and we need to get better at our design. And so it accounted for 7 to 14% of all fatalities, but less than 1% of accidents. So what's that mean? That means that there's a much higher chance of you dying given that an accident occurs, right? So it's if you're looking at it from like a risk management perspective, slope failure accidents are 12 to 30 times more likely to result in a fatality than other accidents, right? So when they do occur, they are significantly damaging to people. So the terms we'll be talking about, one of those is cohesion. So it's the resistance to sliding due to the cohesion or this sort of glue or cement fill within a joint in the rock. So when you see joints in a rock, you'll typically see one of two things. It'll either be an open joint, like there won't be any cementitious fill in there from other rock materials, or you have a closed joint, and that happens a lot. And what happens is, with moisture infiltration and minerals and rocks, sort of within the water, it fills the crack, and then eventually does provide a cementitious like grout on that joint, which then gives it some amount of cohesion, right? So it's glued together naturally. Friction is the resistance to sliding due to the normal force across a joint. So if a joint does want to slide, this is, the reactionary force against that motion. The friction angle, the angle which relates the normal force across the joint to the shear resistance to sliding along the joint. Okay, so think of that as you have the normal force, which is perpendicular to the joint, right? The angle at which the shear resistance to that joint sliding is the friction angle. Here's some typical cohesion and friction angle properties for typical soil and rocks. And so the first sort of slope failure that we're going to talk about is just simple sliding. Okay, so you basically just have the weight of a block on an angled plane, right? And so you have that angle phi, which you have the weight of the block, and then the two components are based on the sine and the cosine of that angle. What amount of force is going, against friction, so to the left and down, and then which one is the normal force, which is perpendicular to the plane. The shear resistance to simple sliding is based on the Coulomb friction criteria. So you have tau, which is friction, or the shear resistance, right? So the resistance is equal to the cohesion plus the normal stress multiplied by the tangent of the friction angle. Okay, and that's how you get the shear resistance. The sliding force, which is going down the plane, right? That's just the block weight, W, multiplied by the sine of the slope angle. So it's the force that is parallel to the plane upon which it's sliding. The normal force, which is perpendicular to that plane, it goes into the plane, is then equal to the block weight W multiplied by the cosine of the slope angle. Right, so we're just getting the two resultant forces. The resisting force multiplied by the area of contact A plus the normal force multiplied by the tangent of the friction angle, which is also equal to W, the weight of the block, multiplied by the cosine of the slope angle, multiplied by the tangent of the friction angle. So that's the resisting force. The resisting stress, that tau letter again, for block sliding is the cohesion plus the weight of the block multiplied by the cosine of the slope angle divided by the area of contact multiplied by the tangent of the friction angle. So that gets your resisting stress. So the safety factor for simple block sliding is then just the resisting force divided by the driving force, and which is the cohesion multiplied by the area plus the weight of the block times the cosine of the slope angle multiplied by the tangent of the friction angle divided by the weight of the block multiplied by the sine of the slope angle. And that would give us our safety factor for simple block sliding. For a dry cohesionless soil, so you have a soil that doesn't have any cohesion at all, right? The safety factor is the resisting force divided by the driving force again, but it can be more simplified in that it just becomes the tangent of the friction angle divided by the tangent of the slope angle. So, if you have a saturated cohesionless soil, the normal stress must be reduced by the pore pressure. So the safety factor of this slope, once we take into account this the pore pressure, it boils down to it's 1 minus the ratio of the density of water to the density of rock, and then that's multiplied by the tangent of the friction angle divided by the tangent of the slope angle. Limit equilibrium. So when your safety factor equals 1, so if the cohesion equals 0, the point at which the safety factor equals 1 is when the friction angle is equal to the slope angle. It's derived here mathematically, but what you end up getting is phi slope angle equals theta, the friction angle. Safety factor, in general, we consider 1.3 stable for short-term stability. Long-term, you should consider a 1.5 to a 2. Historically speaking, when it comes to safety factors, there have been differences in what we considered safe for short amount of time and what we considered safe for a long amount of time. Now, a lot of our empirical design models that we use, we've gotten to a point where we don't differentiate between that as much. However, there still are techniques out there and perhaps even reasons why you would want higher stability in certain areas of the mine, particularly if they're going to be there for a long time. And so slope failure modes. There are multiple types of slope failures that you may see. Plane shear failure, where it fails along the plane. Wedge failure, where a wedge of material fails. A circular arc, which basically, this happens a lot of time, particularly in fills, sometimes in high wall slopes too. But what you'll see is like the bottom, the toe, of the slope, push out. Well, it doesn't have to be at the toe; it could be anywhere along the slope. But the bottom edge of the failure pushes out, and then it sort of just rotates as it falls, right? So you get this sort of circular slip plane, which makes this rotation. And then finally, toppling failure, which is the most likely thing you're going to see in an Appalachian contour mine, a mine that has a high wall. That's the most likely you'll see is toppling rather than the other three. So plane shear failure, strata with a single set of bedding or joints that intersect the slope. Wedge failure, you have to have multiple sets of joints, or bedding, because bedding is a type of joint, right, that intersect the slope. So in a wedge failure, you'll see some joints like this, right, that make a wedge. Circular arc, weak granular material. Remember, like I said, a lot of times this is fill or other broken rock. It could be a coal pile, right? And then toppling failure, strata with columns or vertical bedding and or joints. So here, in our area, we have horizontal bedding, but our joints tend to be vertical for the most part, and they tend to be orthogonal, meaning that they meet each other at relatively close to right angles, right? And so that's pretty common. So that's why you're most likely to see toppling failure in, an Appalachian high wall. So complex block sliding, you can see this all drawn out here. And so there's a tension crack that appears, but it's beyond the crest of the slope. Okay, so it's behind the crest of the slope. And in this case, where this is at an angle, right, you see, it is capable of failing along this surface, right? So here's our slope. We've got a joint through here and a tension crack. What happens? Here's another an example, right? So the tension crack, instead of being back here past the crest, is out in the front. And so that will allow for potential movement of the toe. So if we have a crest crack, the weight of the block for a tension crack past the crest, we have this lovely equation here where we calculate the weight of the block based on the density of the rock, the slope height, 1 minus the crack depth divided by the slope height squared. That gives us a factor that relates this ratio of crack depth to the slope height. And then we have geometrical relationships between slope failure angle and the slope face angle. And it's geometric relations between those to calculate the weight of the block. And if you have no tension crack, a simple block, we've got our density of the rock, height of the slope squared, and then once again our relationship between the ratios of the sines and cosines of the failure angle and the slope face angle. So it's a little bit simpler when there's no tension crack. If the crack is in the slope face, it changes up a bit. We're still using the same parameters. We still have this crack depth to slope height ratio. We have our relationship, our geometrical relationships with the slope face angle and the failure angle. But we also have the failure angle taken into account in this other term here to account for the crack in the slope face. So failure area under the block, that's going to be equal to the height of the failure, or height of the slope, sorry, and minus the crack depth divided by the sine of the failure plane angle. Okay, that'll give us the failure area. Horizontal driving force, V, due to water in a tension crack. So that tension crack fills up with water, now it's got pressure on it, right? V is then equal to the density of the water, divided by 2, multiplied by the height of the water in the crack, squared. All right, so the downslope driving force due to water in a tension crack is equal to the horizontal driving force multiplied by the resultant parallel to the failure angle, right? So this is equal to V, our horizontal driving force, multiplied by the sine of the failure angle, right? So that then gives us that our, we have our water density divided by 2, multiplied by the height of water in the crack, squared, multiplied by the sine of the failure angle, and that's what gives us the downslope driving force due to water in a tension crack. But water in a crack also causes an uplift of force, right? And that is equal to the horizontal driving force multiplied by the resultant perpendicular to the failure angle. So in this case, we've changed our sine to a cosine, and we still have our horizontal water driving force and our failure angle, which is then equal to the same thing all over again, multiplied by the cosine of that angle instead of the sine. So instead of getting the horizontal driving force of the water in the crack, we're now calculating the uplift force. The uplift force on the block due to water is then equal to the summation of the hydraulic pressure along the plane. So we have the density of the water, we have the crack depth, and if we multiply those by the slope height minus the crack depth and divide by the sine of the angle of the failure plane, we then get the amount of uplift force on the block due to the water that's in the system. You can also calculate a safety factor for this complex block sliding with a water-filled crack, and it is the sum of the resisting force divided by sum of the driving force. right? So we have cohesion multiplied by area plus all of this other stuff, W cosine, V sine. That's our water field, the uplifting force, the force that's pushing the block to slide. We also have U here as well, and then tangent of the friction angle divided by, the sum of these relationships. And so that'll give us a safety factor if you've got water filled in that joint. We can also reinforce the slope, right? You can bolt it. You can bolt the slope. And if a bolt is added to the slope, the resultant safety factor needs to add in the additional normal force and subtract the upslope driving force, right? So that has to be taken into account. T being the bolt load, and then theta being the angle of bolt to the failure plane. So that our safety factor is then calculated just like it was before, except we've now added in this T cosine theta and this T sine theta here, based on the angle of the bolt and the angle of the failure plane, right? So there we go. You can calculate a critical crack depth. So if you have a given slope, there is a critical crack location and depth where the safety factor is the lowest, and that depth is equal to the height of the slope multiplied by 1 minus the square root of the ratios of the cosine to the sine of the fracture, or the the slope angle, the face angle, and then multiplied by the ratio of the sine to the cosine of the failure angle. The distance from the crest of this critical crack is then equal to slope height multiplied by the square root of that same relationship. Then we have to subtract the ratio of the cosine to the sine of the slope angle. That'll give us the distance from the crest. The crack depth for an arbitrary distance of the crack from the crest, B, is then equal to the slope height multiplied by 1 minus the tangent of 90 minus the face angle, or the slope angle, plus this B over H, which is the crack location that's arbitrary right at this point, divided by H. And then that's multiplied by the tangent of the failure angle. So, joint slip. Let's look at a sample. This is actually an example test question. The normal and shear force acting on a rock are 10 MPa and 7 MPa respectively. The cohesion and friction angle for the rock joint are estimated at 5 MPa and 25 degrees. Will slip occur along this joint? To answer that, we would want to calculate the safety factor, which is R over F sub S, right, which is equal to the cohesion, which we've got, the area, which we can calculate, plus that normal force multiplied by the tangent of the friction angle, which we have, divided by Fs. So, here's how we do this. So we have 5, which is the cohesion. Area, we're assuming a unit area at this time, plus 10 multiplied by the tangent of 25, divided by 7. Right? Divided by 7. And that gives us 9.66 divided by 7, which is equal to 1.38. So, based on that original 1.3, so no, this should not fail. It should be stable for short-term stability purposes. Okay, another example question. As shown in the figure, the bench face, 75 degrees and 75 feet high, at an open pit mine contains a continuous joint dipping at 45 degrees. Cohesion and friction angle of the joint surface or 10 pounds, PSI, pounds per cubic inch, or square inch, I'm sorry, pounds per square inch, so PSI, and 35 degrees respectively. If the rock has a density of 160 pounds per cubic foot and the weight of a 1 foot section of the triangular block sitting on top of the joint plane is most nearly what? So we have W, our equation, and this gives us all we need to put in here for rock density, our heights, our angle, and that sort of stuff. So here we go. Here's the sort of diagram, 75 feet tall. Here's our joint plane that goes through our slope, and our slope face is 75 degrees. And of course the joint plane's at 45. So what do? We need to put all this stuff into our equation, right? We have 160, our pounds per cubic feet of rock. We divide that by 2. We have our height squared, and then we have our relationships between the cosines and the sines, right? 45 degrees subtract minus 75 degrees. And the weight of the block is approximately 330,000 pounds. Okay, another sample question. If a section of the triangular block weighs 400,000 pounds and the slope is dry, the static safety factor of the slope is most nearly. We have this safety factor equation here that we can use, all right? But we need to know A, which is equal to the height minus the depth of the crack divided by the sine of the failure plane angle, right? So to calculate that, we have 75 for the height, 0 for the crack depth, divided by the sine of 45, and we get that A equals 106 feet. So if we put that into our safety factor equation, we'll have, 10 psi for the cohesion, 106 feet, and then we'll be multiplying that by a 144, right? So we're getting that into square inches from square feet. And then we'll multiply all of that by 400,000, the weight of the block, multiplied by our cosine of 45 degrees, minus 0 sine 30. So there's no water, and it's dry. Tangent of 35, right? It's there. Then we divide everything by the weight of the block multiplied by the sine of 45. And that gives us a safety factor of 1.24. Is that stable? Well, maybe. Maybe is the answer. Generally speaking, we're looking for a 1.3 for short-term stability, but the answer is, we don't quite know. But it does not meet the general criteria. So, another sample test question. The primary effect of water filling the joint plane would be to A, reduce the cohesion by making the joint surface slippery. B, reduce the internal friction by making the rock material more slippery. C, reduce the friction by decreasing the normal forces on the joint plane. And D, increase the driving forces by the normal component added to the water. So let's go through this. It's not A. We can immediately eliminate A because water can affect the cohesion of rock over time, but generally speaking, at least we don't really consider it that way, and that water primarily alters the friction, right? B, reduce the internal friction by making the rock material more slippery. No. Generally speaking, that's not the case. It can over time. I mean, we do experience weathering of rocks. That's not uncommon. But it is not the primary effect of what water is doing. And D, increase the driving force by the normal component of the added water. The normal component of the added water does not add to the driving force. That's what adds to the uplift force. So it's kind of backwards. And therefore C is the correct answer, to reduce friction by decreasing the normal forces on the joint plane. Let's try out this one. A reclaimed waste rock dump consists of cohesionless material with a specific gravity of 2.0, an internal friction angle of 37 degrees. What's the safety factor of the dump slope if it has a uniform angle of 2.6 to to 1, or 2.67 to 1. That's the rise over the run. And so we have the safety factor calculation here, and it is 1 minus the ratio of the densities of the water versus the rock, and then that's multiplied by the ratio of tangents to the internal friction angle and the slope angle, or the failure plane angle, right? So with that, we have 1 minus 1 divided by 2, specific gravity of water, specific gravity of the rock, which was given in the problem. And then we have the tangent of 37, and we divide that by 1 over 2.67, and that equals 1. So we have a safety factor of 1. And so with that, I'm going to close out this lecture here. We've gone over basic slope stability. We've gone over, a lot of the sort of practice problems to help you better understand, what's going on when water's involved, what's going on if there is or whether the crack is filled or not filled. Does the crack have cohesion? Does it not? And that sort of thing. So we've kind of, it's been like a high altitude overview of all of this, but these are the basics, and this is when we expand on slope stability in the rock mechanics class. This is where we're starting from. So with that, good luck on the midterm exam. The rest of the week I will be, obviously available for questions and everything like that. But also I will be doing an update on all the discussions that we've been doing in class up to this point. I'm going to provide my insights into those, and we'll also, maybe go over, some review material as well. So with that, have a great rest of your day, and we'll see you next time.